Welcome to Summarize Science. Today we are looking at a breakthrough in how robots process the world around them. Modern robots use complex models that combine vision, language, and action to perform everyday tasks like picking up objects. However, the researchers found a major flaw in how these robotic brains currently work. As information travels deeper into a robot's artificial mind, it often starts to lose focus on the actual objects it is supposed to handle. Think of it like a person starting a task with high focus, but getting distracted as they think more about exactly how to move their hands. The researchers proved this phenomenon by blinding the model to specific objects at different stages of its thinking process. They noticed that while the early layers are very sensitive to what they see, the deeper layers often ignore the visual details entirely. These results indicate that task-relevant visual cues become increasingly underutilized, which undermines the robot's reliability. To fix this, they created DeepVision-VLA, a system that essentially reminds the robot what it is looking at throughout the process. They use a dedicated vision expert to inject fresh, high-resolution visual details directly into those deep, forgetful layers. This is done through a method that allows the model to share attention between its internal logic and its eyes. But just throwing more data at the robot isn't enough, as too much information can be confusing and slow. So, they introduced a clever strategy called action-guided visual pruning. This system identifies what the robot is focused on and throws away all the background noise that doesn't matter for the chore. By focusing only on the most important pixels, the robot can process higher quality images with very little extra effort. The results of these changes are quite impressive when tested in simulations. Their model achieved an 83% success rate across various tasks, significantly outperforming previous industry standards. It excelled at challenging chores like sweeping dust into a pan or placing items on a rack. Moving beyond simulations, the researchers tested the system on a real-world physical robot arm. The robot was tasked with stacking Coke cans, writing letters on a whiteboard, and even pouring drinks. DeepVision-VLA handled these delicate tasks with much higher precision than the models used previously. In one example, the robot successfully poured a beverage into a bottle with a perfect success rate. The smooth manipulation and successful completion demonstrate that the model effectively attends to critical visual objects. Even when the background was changed or the lighting became tricky, the model stayed robust. This resilience comes from the model's ability to decouple the object it is holding from the messy environment around it. In summary, the researchers identified that robot brains were losing sight of their goals and provided a way to keep them focused. By injecting multi-level vision features and pruning unnecessary data, they have made robotic manipulation much more reliable. This could lead to a future where home robots can handle much more complex and cluttered environments with ease. It's an exciting step toward truly capable and intelligent robotic assistants that look before they act.